Actually here, diffraction, the detailed theory part, how we'll be getting these conditions and all in detail is to understand this, just we need to go through some reference books. Okay, here they have not given it clearly, but for understanding purpose, just let me give you some brief explanation about this. See, if you have, let us say, actually the actual concept of this is, what is diffraction? This is clear, right? So let us start from the diffraction. Diffraction of light. So diffraction is nothing but bending of light. Okay, due to sharp edges, or you can say at the edges of a slit or a hole, or at an object whose size is very smaller comparing with what you call wavelength of light. Okay, I mean it will be almost nearer to the wavelength of light if the size of the obstacle should be. If it is larger, then this diffraction will not take place. So simply we can define what is the diffraction as bending of light around the edges of an obstacle. If it is a three-dimensional, like a circular structure, if we have like this, if this is a circular uh, hole or aperture, when light is passing in three-dimensionally, if you imagine, if light is passing here through this, light rays are passing like this. If this is what do you call a circular hole in a sheet like that, then while coming out, if this is a sheet, let us say this is a sheet, and this hole is there, while coming out, and this is the edge of the circular hole or aperture. So at every part it will bend, it will bend, it will bend, it will bend while coming out. It won't travel just simply directly in straight lines. That what is that? That concept of bending of light at the edges, whose size at the edges of apertures are obstacles. Apertures are obstacles whose dimensions are relatively lesser will be called as diffraction of light. So we can say the bending of light around the edges of an obstacle and entering into the shadow region of those will be called as diffraction of light. So briefly, to understand this, you can let us try to write the definition part. Is that the bending of light? The bending of light around edges of an obstacle or any obstacle around edges of an obstacle when is it traveling or encroaching, either anything you can say around the edges of an obstacle and encroaches into the shadow region of that that object, you can say. Otherwise just can also say or the bending of light around the edges of an obstacle on the encroachment. Encroachment means during the passage, okay, on the encroachment, okay, of light, encroachment of light within geometrical shadow, within geometrical shadow. Geometrical shadow means you can say that the shadow of this object, if it is instead of a hole made here, there is a small object and light is traveling here. Even in this case also just you can understand this, it may bend, the light may bend at the edges of it. So here instead of this, if you, let us say if you are having a slit, if you let us say we have a paper kind of sheet or paper, if you made a slit, this kind of, if you pass the light to pass through this, so at this edges light may bend here and bend here like this, and it will form the called diffraction fringes on the screen. If you keep a wall nearby or anything, it will form diffraction pattern. How this diffraction pattern will looks like, we'll discuss this now briefly. Before that, you need to have an idea about the types of diffraction. Okay, um, types of diffraction. The diffraction is generally classified into two types. One is Fresnel diffraction. Fresnel, here S is a silent, so you have to pronounce this as Fresnel. Fresnel diffraction or diffraction, and, and Fraunhofer diffraction. Fraunhofer diffraction. Fresnel diffraction. What is light? Bending of light when it is passing through an obstacle or an aperture and encroaches into that what do you call the shadow region will be called as diffraction. What is Fresnel diffraction means? In that process, in the process of this, what is bending and something like of light is happening through some obstacle, light should come from some source, some source. So, for example, this if this is your obstacle or an aperture, light is coming from some source. If light is coming from some source and incident on all parts of this is like a circular source, it is coming from some source, and after bending here we are trying to collect this on a screen. This is source and this is screen. If both source and screen or any of these are at finite distance, then the diffraction phenomena taking place in in this arrangement will be called as the Fresnel diffraction arrangement. Or this diffraction happening here will be called as Fresnel diffraction. So we can say the condition for Fresnel diffraction to be observed is either we can say either source of light or screen or both should be at finite distance, at finite distance from the obstacle. This is the obstacle or slit also you can say, whether it is circular or linear slit, whatever it is, at finite distance from the aperture or obstacle, from the obstacle or aperture. This aperture can be circular aperture or linear aperture. Okay, right? So, can say if the source or screen or both are at finite distance from the we can say that obstacle or aperture can be called as a diffracting device. Diffracting device. Such diffraction will be called as Fresnel diffraction. Whereas another one, which is Fraunhofer diffraction, is here the source and screen should be at infinite distance from diffracting device. So that is, say for example, if you are having the what you call the aperture or even linear slit, source should be somewhere at infinity. At infinity means the parallel rays should come here. Parallel rays, the light from infinite source usually will be considered as parallel rays, and then after somehow it has to pass through this, or how that somehow I will give it a little clearly. Then after passing through this, they will bend. Okay, if it is linear shift also will bend, then you have to catch on the screen. The screen also should be at very far away distance, relatively at infinite distance. Then how to catch this is by using lenses. We use lens, and by using this lens, the focus may be somewhere here, but by using this lens, if the light is passing through and falling somewhere here on the edges of this, then they will try to, they used to be collect onto this. Then after passing through this, they may undergo what you call bending through this obstacle. Then it will be again that what you call ejecting light will be catched on this. It may be because it may be on at some far away point. So to collect that, the light is which are coming out, they may go out and they cannot catch. For catching purpose, when they are coming out, the ejecting bended light is when it is coming out. Again we arrange one lens somewhere here, and the light which is bended here and coming out like this, without losing this, we will try to use a lens and we'll try to connect it, and we'll make this to pass through parallelly, and hence we'll collect this on a screen. So this is how we'll do it. So that means we can say that in Fresnel diffraction we won't use any lenses, but in Fraunhofer refraction we use lenses. That is one of the differences you can say. So in Fresnel diffraction, you can also say that um, yeah. Hmm? So you can say that you can also say one more thing, that here in Fresnel diffraction, if you are observing this diffraction of light, so when it is approaching, the light will be treated as a wave, because the source should be nearer by at final distance. If we are using a point source, the wavelets which are approaching this will be in a spherical shape. If you are using a point source, spherical wavefronts will give you what you call will act spherical wavefronts will act as a source of light. Whereas in this case is the source will be at infinity, so the parallel light rays will come here. actually speaking, okay, this is a different thing, but actually just for understanding purpose I have mentioned you this. But usually we will discuss about what you call single slit diffraction. Single slit diffraction. So here how we made this is, instead of making allow the light to enter on this here. So just I have given just like kind of example. Usually what we will do is, if this is an aperture, this is an aperture. So for understanding purpose I have given you that usually the parallel right rays, so many light rays will be there parallel to this, right? So this light rays only will be allowed, parallel light rays only will be allowed. How many rays it can fall on this, those many can be allowed to pass through this, the others you can leave it. So these parallel rays can be treated as the sources of this light is the source of what you call plane wavefront. Plane wavefront. So here spherical or cylindrical wavefronts will be used, here plane wavefronts will be used. These are few points just we have to keep in mind while dealing with this kinds these diffractions, Fresnel diffraction and Fraunhofer diffraction. Okay, so more clearly to understand, usually if you deal with a special kind of diffraction, that is a diffraction by single slit, all these things can be little you can understand it more clearly. Diffraction by single slit, diffraction by single slit, single slit, that slit or aperture, anything you can say. If you take a linear slit, something like this, um, if you have a single slit, for understanding purpose we will representing a little larger in size, but it will be very small in size. If you are dealing with Fresnel diffraction, no lenses will be used. So light will be coming from a point source or any linear source. So spherical or cylindrical wavefront will be we can consider. So number of sources will be there. Number of sources. If it is a spherical wavefront, every point on the what do you call a spherical wavefront which is approaching here will act as a secondary wavelet. So so many sources will be available here. So from these waves will coming here, and they will interfere, and they will give the diffraction pattern. Okay, so if you consider a screen here, if you consider the screen here, and if you also draw a line from the midpoint provided, if the width of this, or you can say size of this aperture or slit is a, then if light is coming from these edges and to this point, central point, they may join, they may meet here with the zero path reference, and it may give what you call uh, bright fringe. But here, somewhere here, if you consider at any point, these light rays, when they're coming and meeting here, not only rays only from this, from every source will come. So here if you divide this to understand this actually the deep theoretical concept, we have to consider a part of the distance in which how many, some number of sources will be there. This will give kind of a small what you call path difference and all, that you have to take mathematically, you have to take it by using integration part. It involves little complex mathematical calculations. So that complex mathematical calculations, I don't want to go into the details of deep details of those. Just briefly, if you consider this is if you divide this into two parts, for example, okay, um, if so a light from each wavelet, as we have discussed already, they will behave like sources. For example, if you consider there are 10 secondary wavelets are there, they will behave like 10 sources of light. So 10 waves will come here. So if you consider a wave from first source, then here if it is 1 2 3 4 5 6 up to 10 are there. Wave from, if this is a fifth source, wave from sixth source if we consider. So if these will come and meet here, they will give a path difference of lambda by 2. The calculations will explain the detailed calculations. And similarly, second one and seventh one will give you similar kind of lambda by 2 path difference. So when path difference is what you called integral vertical can say multiples of lambda by 2 or integral multiples of lambda by 2 or 3 lambda by 2 and so on, you will get in interference you will get a dark fringe. So each pair of these waves will give destructive interference and hence zero intensity, or we can say minima. So that in turn will give you here if you will what you call interference intensity due to a few set of these pairs will cancel out and only a few will give you because of this will get, let us say here diffraction minima, and the path difference condition for diffraction minima will be exactly in reverse way of the conditions of what you call interference maxima. Interference maxima, path difference for interference maximum will be path difference condition for diffraction minima, and path difference condition of interference minima will be path difference condition for diffraction maxima. So these conditions will come as in reverse way. So you can say that for minima, diffraction minima, the path difference here usually if you say this is A, and by symmetry if you consider this is a line here will make an angle theta, and if you want to know what is the extra path, it is given by this one comparing with this extreme sources. If you draw a perpendicular line, this will be the path difference. This is A, this will be A sin theta for these extreme ones. So if this A sin theta, A sin theta is equal to n lambda, then you will get the diffraction minima. But n lambda path difference will give interference maxima. So here it in reverse way. The other minima will give you this way. This path difference give diffraction minima. So from this, if it is nth minima, first minima if you want, it will be 1 lambda. Second minima 2 lambda, and so on. So from this you can also let us say this is equation 1. From this equation, you can also understand what will be the angular, this is theta, right? Angular position at which first diffraction minima will form and second diffraction minima will form. You can find out what angles will form, also can find out. That angular position can also call simply the angle. At what angle with respect to horizontal, first minima will form, second minima will form. So here it may be at some angle, first minima dark fringe may form, the second dark fringe may form, like that. Okay, so if this is let us say this is first this is first minima, first dark or first minima, so for that angle is theta 1. Okay, so if n is 1, and corresponding angle will be theta 1. If this n is some n, you can take it that particular angle n can be theta n, you can take it as. So here theta n gives angular position of nth nth diffraction minimum. So then you can take this angular position by taking sine of the angle as approximately theta for smaller angles. Sine theta is approximately theta. By taking this here, you can write a into theta n is equal to n lambda. So from this you can say theta n is equal to n lambda by a. You will get with this gives you what angular position of, this is equal to angular position of nth, what is the diffraction minimum, angular position of nth diffraction minima. Okay, first minima if you want, n will be equal to 1, so lambda by a. So here you have to also, here itself you have to recollect back that if this is a first minima or first dark diffraction fringe, and if it's at a distance of theta 1, angular position of theta 1, similarly exactly here somewhere separately if you draw, this is the central point at some angular position of theta 1, if you get first dark diffraction dark fringe or first diffraction minima, similarly exactly at same angular position the other side will get another diffraction minima, first diffraction minima. So the separation between these will be called as here, that means hereafter you will get first dark, hereafter you will get first dark, means this entire space will be occupied by central bright fringe, or you can also say primary diffraction maxima. This will be called as primary diffraction maxima or primary maxima. Diffraction maxima or maxima. So the width of this primary diffraction maximum will be equal to, in terms of angular position, theta 1 plus theta 2 will give you this entire width. Entire angular width we are telling. So you can say that I can also say width is equal to 2 theta 1. That is one thing you have to understand. Another thing is, if the position of what do you call lateral position of this minima, diffraction minima is y. For first one y1, second one y2, and so on. For nth one, if we take it as yn, then how to, this is the angular position of nth diffraction minima. Later, if you take this as lateral position of nth diffraction minima, how to find this? Let us try to see what should be the what you call lateral position of nth diffraction minima. Lateral position of nth diffraction minima is to find the lateral position. Lateral position can be expressed as y. For a lateral position of nth diffraction minima, when you say here itself, otherwise you can write it as yn. You guys remove this here. Okay, it will be yn. How to get this yn? For this, let us make use of equation 1. Let us say this angular position is equation 2, this relation is equation 1. For equation 1, you can say, equation 1 says a sin theta n is equal to, or theta is equal to n lambda. But this, for smaller angles, we can say sin theta is approximately equal to theta, and tan theta is also approximately equal to theta. So we can say sin theta is approximately equal to tan theta. So in this what you call representation, if you say this is central part, as if it says O, okay, and this is, if you say this point is P, this point is Q, then OPQ, if you take it as a right angle triangle, provided if the screen is at a distance D from the slit, then tan of this theta is equal to opposite side by adjacent side, that is y by D. Okay, so from this you can take a sin theta approximately equal to tan theta, it is equal to y by D. So here, if this y represents nth position, lateral position of nth minima, diffraction minima, then if you substitute this here, tan theta yn by D here, then you will get, this implies a into yn by D. Yn of D will take this. That means nth lateral displacement of nth dark fringe or nth diffraction minima, dm, diffraction minima. So it is equal to n lambda. From this, we can also express this position as yn dm, that is diffraction minima. Position of nth diffraction minima is equal to n, this capital D comes here, it becomes d lambda by a. This is very important relation. Okay, if you want the first diffraction minima, second, third, and so on, that will keep y1 first one, so it is equal to d lambda by a, and second one can be taken as 2 d lambda by a, and so on. Nth one is n d lambda by a. Here again, if you get into this diagram, so from here to here we have taken yn, right, from center to this d1. If this is first dark, from here to here you can take it as y1. Similarly, from here to here we can take it as y1 only. Okay, so that means width of the primary primary diffraction maxima, primary maximum will be 2y1. In terms of lateral displacement, you can take this as, from this implies, you can also say width of, here you can draw this diagram, similar one. If this is a central line, if this is a screen, if this is theta 1, if we have formed first dark or first diffraction minima at a lateral distance of y1, similarly at a similar lateral distance of y1, if you at this side also you will get what is that, first dark or first diffraction minima at same angle theta 1, then you can take the width of this is given by y1 plus y1 2y1, width of primary maximum. So width of primary maxima or diffraction maxima is, you can say W is equal to 2y1, but y1 is position of a first diffraction minima d lambda by a. Substitute this here, you can write it as 2 d lambda by a will be the width of primary maximum. And if you observe, this will be the what a maximum width it will have. Another secondary maxima width will be 2 d lambda. Position of the first minima is this. Then next comes primary. This is primary minima. Sorry, this is primary maximum. Then comes here a dark fringe or minima, diffraction minima. After diffraction minima, one more maxima will come. Those maximas are called secondary maxima, secondary diffraction maxima. This is primary diffraction maxima. You can also write this as here. This is primary maximum is a bright fringe. So after this first dark fringe, diffraction minima, again maxima comes. That will be called as secondary maxima. So how to find the positions of those secondary maximas? Position of uh, secondary maxima is given by, so just like how we have understood that position of minima from this condition, path difference condition, this one same way you can get that. So what is that? A sin theta is equal to path difference for minima in diffraction should be n lambda, for maxima it should be 2n minus 1 into lambda. So what you have to consider here is path difference. What is that? A sin theta should be equal to 2n minus 1 into lambda by 2 we have to take. From this, again by substituting sin theta as yn of maxima, not minima, maxima, that is bright fringe, divided by capital D gives you 2n minus 1 into lambda by 2. From this, you can say nth maxima, we call it a secondary maxima actually. SM you can take secondary maxima. So position of nth secondary maxima, first secondary maxima, second secondary maxima, like that, are given by 2n minus 1 into d lambda by 2a. So this is again another important one. If you here we are every point to point we are not discussing that clearly, but if you observe the positions of all this, first no, secondary maximum where you will get n is equal to 1. N is equal to 1 means becomes 2 minus 1 is 1 d lambda by 2a. So you can write here secondary maximas and minimas. Secondary maxima position is given by yn is equal to 2n minus 1 into d lambda by 2a. For this it is given by yn is equal to what? N into d lambda by a, nth maxima, n into d lambda by a. Here if you want first one, that is the first secondary maxima is equal to d lambda by 2a. Similarly, first minima will be at d lambda by a. D lambda by a, it will be d lambda by 2a. And then this second one will be at 2 into 2, 3. So we'll get 3 d lambda by a, 2a. So or you can also write it as d by a into lambda by 2, d by a into lambda by 2, d by a into 3 lambda by 2, like this you will get these positions. You can also write in that way. So similarly for this it is y2 is equal to 2 d lambda by a. So here d lambda by a, here this will be d lambda by a by 2. That means at a half distance we will get a secondary one. So from there the what you call you can say that primary maximum will start. This we can in wave form, if you want to express like this, you can express. If this is a central maxima, we'll be having maximum actually in intensity, in the form of intensity. This is the intensity of this central one. Again that part we are not dealing here in detail, but for understanding purpose it will be what you call, it is occupying larger space, so most of the intensity will be accommodating in this. So its intensity will be more, primary maximum intensity. Then it decreases and becomes what is this, minima. Then again secondary maxima will come here on both sides. and again minima will come. This minima, after this minima, again the next secondary maxima will come. So these secondary maximas intensities will decreases gradually. This will decreases gradually. So here this will be the width of what you call primary maximum. So it is equal to, already I have expressed, right, 2 times y1, etc. So this is how it looks like. This is briefly about how to find the lateral positions and angular positions of this without using lenses. But here they have used by what is it, Fraunhofer way, by using plane wavefront, somehow by using plane wavefront. Then for this to undergo diffraction, we have to use a lens actually very closer to the slit. Then only they will form the, what you call, they will bend the light rays again further and form the final refringes on the screen. To bring the final interference onto the screen, we have to use a lens in form of a diffraction. Okay, so that is the difference. That means the focal length of this will be equal to the distance between the slit and the screens. Okay, so by make simply, you can make use of this, and you can work out some numericals. So let's try to go to some numericals. This part we'll see afterwards. Ninth one. What is this? Two lateral triangle. Two coherent monochromatic light sources are located at two vertices of equilateral triangle. Okay, two coherent sources. If the intensity due to each of the source is independently is 1 watt per meter square, if intensity due to each of the sources, intensity of this one and this one is 1 watt per meter square. At intensity due to each source independently is, that is I1 and I2 is 1 watt per meter square at third vertex, then the resultant intensity due to both sources at that point is, that is at the third vertex is. Intensity is given, numerical value. What is the resultant intensity you are asking to find? Right? So let us consider that. It is a equilateral triangle, right? Let us consider, you can consider equilateral triangle like this, or like this. Either way you can consider. Okay, let us consider the base is like this, looking like this. This is the base of equilateral triangle. Okay, and another vertex is here, so that this is one vertex, this is another vertex, this is another vertex. Okay, so here let us say there are two sources, S1 and S2. We are discussing about what? Interference. Okay, the question is, two coherent monochromatic light sources are located at two vertices of equilateral triangle. Two sources are here at two vertices of equilateral triangle. Equilateral triangle. If the intensity due to each of these sources, if you say this is I1 and this is I2, so the intensities are equal, I1 equal to I2 equal to, let us say, I0, which is equal to 1 watt per meter square at the third vertex. When they are coming here, at this point they are equal to this much. Okay, at the third vertex, then the resultant intensity due to both the sources at this point. What is the resultant intensity here is the question. What is the resultant intensity here? We know that resultant intensity due to interference of two waves is IR is equal to, if the intensities of individual waves are equal, is equal to 4 I naught into cos square, what? 5 by 2. Yes or no? Cos square 5 by 2. Uh, cos square 5 by 2. Here, okay, if this is what you call equilateral triangle, length, side length of every side will be equal. Okay, so we can also say, if you draw a line from the midpoint of this to here, so the to the vertex, so this side, this length and this length will be equal. So the this length and this length also equal. So we can say path length of this source and path length of this source will be this way. The travel will be equal. So path difference of these two will be 0, right? So this phase, if you write in terms of path difference, can we write like this? 4 I naught into cos square. Phase difference is 2 pi by lambda into path difference, right? Right. Anyway, path difference is directly also you can write it is a pi by lambda into path difference here, because of that 2 pi 2 gets cancelled, but path difference is 0. So phase difference also will be 0 directly, also you can take that if exactly if you want. So this is path difference. In terms of path difference, this path difference is 0, cos 0 should be equal to 1. So can you take IR is equal to 4 I naught into 1, where I naught is given as 1 watt per meter square. Sorry?
4 So the answer 4.
Question number
9.
9. So we'll get 4 only, right?
Yes.
So it is equal to 4 into 1. So resultant intensity will be equal to 4 watt per meter square. That's it. Right?
So then this sum. So fourth sum, sir. So actually we are getting the answer, but they have given us this first option. We are getting like for first minimum we are getting 0.625. Then for second like we are
The
getting in
order is
opposite direction.
changing. So we have to take little careful. So, but those kind of options are not there in other values,
Actually, they
right?
are asking the positions of the first three minima, sir. But in him they are giving for minima n lambda d by d. Something
This is, the diffraction or interference?
interference, sir. Actually, we have to consider 2n minus 1 by 2. So in that case, we are getting options like
1 second. In the double slit experiment, the slit separation is 0.2 centimeters and the slit to screen distance is 100 centimeters. The positions of the first three minima, if wavelength of source is this. First three minima will be 2n minus 1 into lambda by 200, right? So question number 4. The question is, in a double slit experiment, the slit separation will be taken as d is equal to 0.2 centimeters is equal to 0.2 into 10 to the power minus 2 meters. And the slit to screen distance, that is capital D, slit to screen distance is 100 centimeters. 100 centimeters is equal to 1 meter. The positions of first three minima. Positions of first three minima. Positions of first three minima are equal to what? Positions of y1 minima, that is a dark, y2 dark, and y3 dark are equal to what? So we know that position of nth minima, nth dark minima means dark fringe. The positions of first three minima if the wavelength of the source is this. Double slit experiment. You have to get interference minimum and nothing but dark fringes. So it is equal to 2n minus 1 into lambda by 2 y is nothing but into d lambda by 2d, right? So we can say y1 is equal to 2 minus 1 is 1.
1.
So d lambda by 2d y2 is equal to 2 means 2 into 2 4 for minus 1 is 3d lambda by 2d and y3 is equal to 5d lambda by 2d. So if you simplify this, we get d is 1, lambda is what is given 500 nanometer. It is also given that lambda is 500 nanometer. Nanometer is equal to 5 into 10 to the power minus 9 plus 2 becomes minus 7 meters. So 1 into 5 into 10 to the power minus 7 by 2 into small d is 0.2 into 10 power minus 2 or 2 into 10 to the power minus 3. 2 into 10 to the power minus 3 minus 4 remains here. 5 by 2 is equal to 2.5 into 10 power minus 4 meters or 0.25 0.25 millimeters. Point. Let me if you want in centimeters, two decimals you have to take it. They have given centimeters, right? So two decimals comes means 0.025 unit. It is equal to 0.025 centimeter. First one. So second one, actually it is a
Sir,
D.
actually 2 days, sir. So 2 into 2 into
This is the one, right? For first one, n equal to 1, 2 into 1 is 2. 2 minus 1 is 1.
So actually y1 is equal to d lambda by 2d. That
So
d is
this,
equal to 2 into 10 power minus 3.
okay, okay. Here one more 2 is there. Okay. D value is this. So 2 into, okay, 2 into means divided by 2. Divided by 2, right?
Yes, sir.
Divided by 2. So means this is equal to 0.0125 centimeters. 0.1025. What is 0.025 centimeters means 0.0125. Then it will be in all in centimeters only, right? 0.025 0.125 millimeters. The units conversions, look into this carefully. So by 0.2 means hmm, actually 5 by or 2.5 by 2, 10 power minus 4. So it should be, so what you are getting, it is equal to point, sorry, 1 point only. Sorry, I did something wrong here, right? Yeah. So it is a 1, it is equal to 1 point. Let us remove all these things here. It is equal to 1.25 into 10 power minus 2 meters. It is equal to minus 4 meters or 2 decimals means 1 2. Zero coming, right? This 10 power minus 7, minus 7. Let us check here. D is zero point 0.2 in centimeters. 0.2 in 10 power minus 2. 0.2 centimeters. 0.2 in 10 power minus 2 or 2 in 10 power minus 3. 2 in 10 power minus 3. D is 100 centimeters, so 1 meter. Lambda is 500 nano, so 5 into 10 power minus 7. That's it. Y1, D, Y, 5 into 10 power minus 7 by 2 into 2 into 10 power minus 3 minus 4. So 5 by 4. Why the decimals were not confusing here? Okay, they are doing correct or the options are correct or we are correct?
Options are so because they have taken the maximum.
The positions are first the minimum. Okay, if you take that way, they are getting these options, right? So position.
So because of that, we get lambda
Mm, mm,
and
mm, mm, mm.
so then
The positions are first three
and the option of as
minimum.
that form using that formula we can answer for the bottom.
Yeah. So the question maybe
So let's try for another two.
the printing mistake. It should be minimum is this only. Maximum means you have to take it as n lambda. This is the same thing. You can cross check by using the same.
So
Yeah. What is the one?
that's it. So that's
Yeah.
thank you sir.
One minute.
Then option for the class.
Hmm. One second.
16.
16th number. So the question is, okay. So next question number 16. So it is given that question number 16, page number 231. It is given that a small aperture is illuminated with a parallel beam of wavelength lambda is equal to 628 nanometer, means 628 into 10 to the power minus 9 meter nano. The emergent beam has an angular divergence of 2 degrees. Angular divergence means theta is equal to 2 degrees. The size of the aperture is, so in a diffraction pattern, if it is angular emergence of emergent beam is having angular divergence means from parallel, what if you say it is something like if we are having a slit, if light parallel light beam of light incident on this, are you getting this? Here, because of bending property, it will diverge from its direction through some angle. That angle is called divergent angle. The emergent beam has an angular divergence of this theta. This theta is 2 degrees. Instead of passing directly, it bent by the 2 degree theta, that is equal to 2 degrees. Right? This, if so, what would be the size of this aperture? Usually, let us consider the size of this aperture is A. Hmm? So already if you have considered that, what is this path difference relation? Here is, what is that? A sin theta is equal to, for what is mentioning for minima, for diffraction minima is n lambda, right? Anything is mentioned about this here? So emergent beam has an angular divergence, lambda is given, the size of the aperture is asked. So it is not mentioned anything about the formation of a minima, first minima, second minima, like that, right? Hmm. So if usually it should be mentioned if it is for first order minima, if because of this divergence, if it is forming a what you call a minima at some angle, then you can make use of this relation and you will get this. So in such case, if that is the case, then you can say A will be equal to A will be equal to, if it is first order, then it will be 628 10 to the power minus 9 by theta is given in degrees. To get this in meters, you should have theta in radians. You have to convert. Okay, if you consider if it is for first order, for example, actually, if this kind of questions comes, means whether can you deal with this or not, let us check once. So if theta which is equal to 2 degrees. If you want to convert this into radians, what to do? Pi by
180.
pi by 180. So we'll get pi by 90 radians, right? Radians. So if you replace this theta with pi by 90, then you'll get A is equal to 628 into 10 power minus 9 by pi can be expressed as 3.14. 3.14 by 90. So you can take it as you can take 19 here numerator, right? And simplifying this further, what you can write, 628 into 90 by 3.18. 628 into 90. 628 into 9. Something wrong with this. 628 into 9. 6. 2 times. Yes, you can directly take it. If it is 314, if you multiply here by 100 by 100, it becomes 314, right? So you can also mention this as 100 by 100. Then you can write it as 628 by 314 into, it becomes 9 into 10 to the power minus 9 plus 3 minus 6 by 100. So this becomes 2 times 314 628, 2 times, right? So it will be 18. This plus 2, if for this we have multiplied, so that means here we have that is plus 2. So you get 18 into 10 to the power minus 4, you will get minus 4 meters. So minus 9 is there, right? Hmm. This is minus this is 10 power. Here we are multiplying this 100 with this, so it will become 3.314. Here 100 will be there as it is. So 9 into 10 power 3. So 10 power minus 9 plus 3 becomes 10 power 6 only. Minus 6 only will remain here, right? So directly can write it as 18 into 10 power minus 6. That is micrometer. 18 micro. Hmm? Mm-hmm. So I think this here actually they have taken as n pi by this, right? There is something. It is the data is missed here. If it is supposed to be something like here, if n is there, if n is 2, then you will get it, right? So that means the data should be missing here. It should be something like second minimum. The emergent beam has an angular divergence of 2 degrees for second minimum. For second minimum, then you will get this. So they have given in the data, but they missed in the question. That means while copying this, some typing mistake might have happened. So that is what is missing here. Okay, that you have to understand. So for this will be the aperture size, 18 micrometer. Fine. Right. That's it.
Thank you.
Interference in white light. That is actually this first violet only come here nearby. There is actually printing this 34. Each deposit experiment, the distance between two slits is this, the distance between slits is the screen is this, and the wavelength of light is this, intensity of the wavelength on the screen is 75% of the maximum intensity. What is the smallest distance at this point from the central page? Yes, see, it is a previous years, the previous year of KVPY question. So the question is In Young's double slit experiment, the distance between two slits, will take it as small d is equal to 0.1 mm, is equal to zero point 0.1 into 10 power minus 3 or 1 into 10 to the power minus 4 meter. The distance between two slits is this. The distance between the slits and the screen is capital D. It is equal to 1 meter. And the wavelength of the light used is lambda is equal to 600 nanometer. Can be expressed as 6 into 10 to the power minus 7 meters. The intensity at a point on the screen, if this is a double slit, say this is a screen, due to the light from here, somewhere here, we say the intensity at a point on the screen, at some point P on the screen is IR, let us say it is IR2 is equal to 75%. 75% means by 100 or 0.75 can take. 75% of maximum intensity. That is intensity, let us say this is IR1, this is IR2. IR1 will be 4 I naught. 4 I naught. IR2 is equal to 3 I naught. So it will be 25 3 by 4. 3 by 4. 3 by 4 into 4 I naught. So 4 cancel, it will be 3 I naught. IR2 equal to 3 I naught. Where the intensity at a point on the screen is 75% of the maximum intensity. What is the smallest distance of this point? Let us say this point is y. This distance is y. How can you take this? How can you take this? IR2. Let us say directly IR2 by IR1 is equal to 4 I naught by 4 I naught. 4 I naught into cos square. In terms of path difference is not mentioned here. Okay, let us say it is pi by lambda into delta x by central fringe. Central fringe path difference is 0. So you have to take this as 1. So this will get cancelled. So from this we can say IR2 is equal to IR1 into cos square. Let us bring this. Let us keep this as IR2 by IR1 only. This is equal to cos square of pi by lambda into delta x. So, but here intensity at this point is 75% of this. So 75% of is 0.75 by 4 I naught. This is 4 I naught. 4 I naught, 4 I naught to cancel, you get 75. This is 0.75. This is 0.75. So this is equal to 0.75. So 0.75 you can write it as something root 3 by 2. Root 3 by 2. Is it root 3 by 2? You have to cross check. Or pi by lambda into delta u is equal to root 3 by 2. We can yeah. So pi by lambda into delta x. Actually, cos square of this equal to root of this. So 3 root of 3 by 4 becomes root 3 by 2. So this will, if this is root 3 by 2, this angle part, this angle gives here path difference. So from this you can say path difference delta x is equal to lambda by pi. Lambda by pi into root 3 by 5 by 6. Cos inverse of this, right? So cos inverse of this gives us so actually pi by lambda into this, cos of pi by lambda is root 3 by 2. Cos of pi by lambda is this. So pi by lambda equal to cos inverse of this. So pi by lambda, this implies into delta x is equal to cos inverse of root 3 by 2. That is equal to 5 by 6, 30 degrees is 5 by 6. So 5 by lambda into delta x is equal to this. 5 by cancel. So from this we can we'll get delta x is equal to lambda by 6. Let's say this is 1. But the question here is, what is the smallest distance? Where path difference is this? So we also know that delta x is equal to d into sine theta is equal to d into y by capital D. Y into capital D. So let us say this is 2. From 1 and 2, we can write d into y by d is equal to lambda by 6. So from this you can say y is equal to d lambda by uh, d into 1 by 6. So here this values are given, small d, capital D, everything is given, right? Lambda, everything. Substitute the values, then you will get. Substitute the values. Okay. Hello. 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 Class class 9 o'clock చేస్తారా ఇప్పటికి చేస్తారా న్యూస్ చూస్తారు ఇక్కడ న్యూస్ అప్పుడు చేయి ఓకే సరే actually this we missed to discuss this point, man. The missing wavelength part. Hmm. Okay, actually, yeah. So, actually, here just you need to have an idea about this missing wavelengths. Missing wavelengths when if you are observing what you call the fringes in just in front of the slit. Say for example, if you are having a double slit and a screen, this is slit 1, this is slit 2, provided this is the midpoint of the slit if you consider this one as the central part. Okay, and if you are observing the fringes at a point in front of one of the slit, means in front of this means if you take this light here, so it will travel exactly the distance which is equal to separation between this. But if a light is traveling from here, then you can take the distance is this S2P if you consider this is a point P, right? Then what you have to remember here is if the distance between or separation between the slits is small d, this is capital D. So if you consider some point P on the screen and if it is at a distance y from the central bright fringe, then right, the path difference between these two waves interfering here can be S2P minus S1P. S1P is directly D. Yes. So then what should be S2P? How can you write this to understand this? Let us also consider one more dotted line here. By symmetry, if I draw a line here and if it is making an angle theta, this also will be theta. Right? If this is D, if this is Y. Yes. So I can say this is D, this will be D by 2. Yes. So this entire thing is D, right? So this also will be D only. This entire thing will be D only. If you consider this is some other, this is P, this is P, and let us give some names to this. Uh, A, B, P is a right angle triangle. From this, this path length AP is equal to S. Oh, you have taken S2, right? Let us take it as S2P, and this point here it is S2 is there. So S2P PQ, let us take here. Hmm? S2PQ is a triangle. In this, the path length S2P is given by, from the triangle, is the hypotenuse of the triangle. So it is equal to square root of side square plus side square. This is one side and this is another square, and another side. From this we can say the path difference delta x is equal to S2P minus S1P. Got it? Where you can also write delta x is equal to S2P is nothing but square root of, what you can write? Square root of uh, d square plus small d square is S2P minus S1P is directly d only. So this, if you simplify by taking this capital D out, if you take capital D out, it becomes a D square. D square, if you take it out, it becomes D. Then you can write this as D into square. This is square root. You can write it as a power half. Then you can write it as 1 plus small d square by capital D square over half minus D. So by using binomial approximation, binomial approximation, you have to write here from. What is this binomial approximation? We can say 1 plus x power n can be taken as approximately 1 plus nx. So if it is minus 1 plus x power minus 1, 1 minus nx. Or if it is 1 minus x power n, 1 minus nx. Like that, you have to understand. You should remember this. By making use of this, you can write this as delta x is equal to d. D is common here. Can t again, if you take this out, you can write this as 1 plus d square by 2d square minus 1 minus 1. This will get cancelled now. Then you'll get, this is what, small d square. So and here if you multiply with this dd gets cancelled. Then you'll get small d square by 2d. You will get, this will be the path difference in this case. If delta x is equal to small d square by 2d, and if you take this as equation 1, but in general, okay, here if you consider for forming bright fringes and dark fringes, different cases will come, right? If you are missing the wavelengths, means you will get a dark fringe, right? So for missing wavelengths, intensity will be 0. That's what you have to remember. Intensity is 0 means dark fringe will be getting. Okay, the dark fringe you are getting means like the corresponding path difference should be 2n minus 1 into lambda by 2. That is what you have to consider. So what you have to consider here is for missing wavelengths, intensity will be intensity will be will be 0. That is, we will get dark fringe. That is, it gives dark fringes. It gives dark fringes. That implies path difference for dark fringes will be 2n minus 1 into what, lambda, only path difference. So 2n minus 1 into lambda by 2. Let's say this is equation 2. So usually in such case we are getting this path difference. So in this case to find the missing wavelengths, you have to equate this path difference obtained in this case with what do you call it, destructive interference path difference, that is equal to this. So we equate this to 1 and 2 implies, if you equate them, we'll get d square by 2d will be equal to 2n minus 1 into lambda by 2. We want to find that missing wavelengths, right? So from this, what you can say, the wavelength lambda should be equal to, this implies lambda is equal to, this 2 goes here, so 2 small d square by 2d into 2n minus 1 you will get this wavelength here. That means where n is equal to 1 to 3 and so on. So these wavelengths will, where n is equal to 1, 2, 3 and so on. If you give 1, if you give 2d square by 2d, 2 gets also gets cancelled, right? So 2 gets cancelled. So you can say lambda is equal to small d square by d into 2n minus 1, where n is equal to 1, 2, 3 and so on. These wavelengths will miss. What are those? If you say n is equal to 1 d square by d, n equal to 2 2d square by d, 3d like sorry, divided by lambda, we are getting, oh, divided by, okay, okay, it's little small mistake again. Not in numerator, you have to get this in denominator, right? So from this, what you have to understand is, from this lambda, from this implies lambda is equal to 2 goes to numerator, this comes to denominator, 2 small d square by, or here itself you can cancel this 2 2, can cancel this 2 2, you will get d square by 2n minus 1 into capital D, where where n is equal to 1, 2, 3 and so on. That means the wavelengths of that means lambda is equal to, for n is equal to 1 d square by d, and n equal to 2, 2 into 4 minus 1 3, so d square by 3d, for 3 6 minus 1 5, d square by 5d, like this. What you call this 1 by odd integer multiples of d square by d's wavelengths will miss. So these will be called as missing wavelengths. Okay. So so whereas okay, what else we can say here? If you put 1 2 3 and so on, you'll get these are the missing wavelengths, right? So in the, if same thing, we can say uh, if bright fringes are to be formed exactly opposite to S1, then if you want to find missing wavelengths, you have to equate the path difference with the 2n minus 1 into lambda by 2. Whereas which wavelengths, which bright fringes of what wavelengths will form? If you want to understand that, you have to equate this. Then you can say that you can say the bright fringes with these wavelengths will present. Wavelengths missing means we use dark lenses. The presenting wavelengths. The present wave, which presenting wavelength means the fringe which is having, we are getting the fringe means, bright fringe means it will be having some intensity, and hence it will be having some wavelength. That wavelengths of present what do you call it? Presenting fringes will be expressed as the other way, by taking this path difference equal to n lambda. So yes, even multiples of d square by reciprocal of even multiples of d square by d, so you take it. Okay. That's it. Yes, yes. One second. Let me end this.